derivatives of exponential and logarithmic functions. So to start, I felt like it was good just to talk a little bit about the number e. The number e is the natural base for natural log and e to the x. It's a number. It's an irrational number, just like pi. And if you plugged it into your calculator, it's about 2.71828, blah, 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 blah. But it's a number. It's an irrational number, but it's a real number. When you first learn about pi, you realize that pi was discovered when they were working with measuring the circumference of a circle, and that it's the ratio of the circumference divided by the diameter, which is a much easier sort of discovery of pi. E has other definitions and was discovered its natural reoccurrence by looking at a couple of different things. One, the definition of E is the limit as n goes to infinity of 1 plus 1 over n to the nth power. This is the definition of E. If you plugged this expression into your calculator, it would be approaching a horizontal asymptote equivalent to this 2.718 number. E is notable in terms of derivatives because its slope is always its y value. So E is the unique positive number for which the limit as h approaches 0, that should be throwing a little red flag in your head. The limit as h approaches 0, e to the h minus 1 over h equals 1. When you hear the limit as h approaches 0, it should make you think of the definition of the derivative. The definition of the derivative, I'm just going to sneak it over on the side here, is the limit as h approaches 0 of f of x plus h minus f of x all over h. Luckily, in BC Calc, you're never going to be forced to evaluate a derivative by using and working out the limit. However, you are going to be forced to recognize limits in the form of this definition and have to say, hey, doesn't that mean derivative? And then you can utilize your shortcuts. But you have to kind of be triggered to think, oh, they want me to take the derivative by seeing this limit as h approaches 0. So let's kind of match it up a little bit. Why am I saying that this is a derivative? Well, the limit as h approaches 0 is what kind of tipped it off for me. But now I've got f of x plus h. Well, all I see is e to the h. So the only way that this could be true, that it's a derivative, is if the function f of x is e to the x, because I see e to the h, and it has to be at x equals 0. Why does x have to be 0? Because it's missing. In order for x plus h to just be an h over here, would have to be that I was adding 0, and that's why it could just disappear. So this is like e to the 0 plus h, which is why it's just e to the h. I'm going to erase that underline that I have under that h because I felt like kind of hard to see. All right, so what's that 1? Well, it's supposed to then be minus f of x. Well, if f of x is e to the x, and we're saying at 0, e to the 0 is 1. Anything to the 0 power is 1. So this 1 is actually e to the 0. And so here's where I'm saying that e is unique because its derivative, this is really asking me for the derivative of e at x equals 0. The derivative is equal to 1, and so is its y value equal to 1. Now, this is just specifically at 0. That's actually true for e at any value of x. Its derivative, or its slope, is always the same as its y value. So that's something notable about E. And then the last one, we're really not going to talk about this one till the end of the year, but I kind of felt like I couldn't leave it out. If I'm giving you all the definitions of E, I might as well put the summation one in here. This is a series, an infinite series. And this would be what we sort of culminate the course with infinite series. And E is the summation from 0 to infinity of 1 over n factorial. I'm going to leave it at that. I'm not going to explain that any further because we'll get there, but at least you kind of have them all together. None of these limits you have to necessarily have memorized. I felt like it was a good introduction as to what is E and how is it related, because much of calculus is going to be in terms of E, where we're going to be using things with the natural base and the natural logarithm. What the lesson really is going to be about today is how do we take its derivative by our shortcut rules? What is the derivative of e to the x? So we do have to memorize. And we have to sort of be preparing ourselves for back to normal during AP time. Because if we are back to normal, when you take the AP exam, there are no formula sheets whatsoever provided for you on the AP exam. All rules, everything you've learned has to come with you in your brain. So derivatives, these rules, you have to have memorized. With that said, at the end of last year, everything turned out to be online and it was open notebook. So that whole preparation kind of went out the window. If that's where our exam starts to go, it will ease up on our memorize and maybe kind of fine tune our note taking. But we're going to make sure that we're kind of preparing for that scenario where you have to have this all memorized. So I've said it in words that E has a slope that's equal to its y value, which means its derivative is equal to itself. So the derivative of e to the x is e to the x. Its y value is equal to its slope. The function is equal to the derivative. How could that become any more difficult? Well, chain rule can make an appearance. What if it's not e to the x and it's not just an x? What if it's e to the x squared plus 7 or e to the sine x and there is a function composed inside that exponent? Well, that's chain rule, how we handle a derivative of a function and a function. So if we let u be a differentiable function of x, then the derivative of e to the u is itself e to the u, but then times u prime, which is the derivative of u. And it's really just the chain rule built into that the derivative of e is itself. Now, it's great that we're giving e special attention. It deserves it. But we could possibly have a different value as the base b. What if we had the exponential function 2 to the x or 1/2 to the x? It doesn't always have to be the base of e. So our second rule here is for b, where b is equal to any real number. Well, the derivative then of b to the x, it starts off as itself, b to the x, but times the natural log of b. Now, arguably, e to the x is following that same rule. If I said that the derivative of e to the x, and I followed the rule for b to the x, it would be e to the x times the ln of e. What's the ln of e? 1. So e to the x just gets all of this special attention because it is the natural base, but that's really just 1 in disguise. So it's a specialized case of b to the x. And again, we could sneak in a chain rule. If u is a differentiable function of x, and we have b to the u, which maybe is, for an example, just to make sure everyone's understanding all these letters, let's say it was like 3 to the x squared minus 5. That would be a b to the u, some real number as a base, and then function of x in the exponent. Then we've got b to the u again, times the ln of b, times u prime. The u prime, the derivative of u, is really the chain rule built in. Questions? Let's do some examples so we make sure everyone sees how this is all going to come together. All right, number 1. Find dy dx. dy dx obviously is notation for the derivative. And I give you y equals e to the x plus x squared. So that's my u. I don't have just an x in there. I have an x plus x squared. So this has to follow the derivative rule, e to the u. So my derivative, dy dx, following the rule, is e to the u again, so as is, but then times u prime. So I just have to zoom in just to that x plus x squared and multiply by its derivative. So it's a little power rule, 1 plus 2x. And that's the derivative. It's really about being able to memorize and execute the rule. All of your derivative shortcuts are shortcuts for that limit definition of the derivative, but certainly the better thing to focus on because the limit definition is always a pain. Now, I'm going to push the level of examples. All right, and I think that's what you're going to find one of the biggest difference between last year and this year is the level of difficulty in each of the examples. So let's take a look at number 2. All right, first of all, d dt, so there's a change in variable there. However, the change in variable stays throughout. So I'm still taking the derivative with respect to t of a function in terms of t. So I'm not bringing up anything like you might recall from last year about related rates. Nope, this is a t with respect to t, so I was just trying to trick you with the change of letter. The problem is that I can't jump right to this e to the negative t. I have to look at the function as a whole. What rule actually has to start off this derivative? What's the bigger picture here? Chain rule. This whole thing is squared. So I just have to start with my outside-inside rule, which is the chain rule. And I have to start by taking this 2, multiplying it down. When you're doing the chain rule, nothing changes inside the parentheses. Just for fun, I'm going to write to the first power just so everyone knows that I had to think about subtracting 1 from the exponent. And it's not until after I take care of that squared that now I have to zoom in and take the derivative of what's inside the parentheses. So this e to the negative t, even just a little negative sign turns it into an e to the u. So the derivative of e to the negative t is itself e to the negative t, but then times the derivative of u, which is negative 1. You could always just sneak it in front as a negative sign. I'm just trying to be the most clear as I can in notes, especially that we have people at home. Plus, now since I have to put a plus sign, I need to make sure I group this together with parentheses because this is this plus, and then the derivative of e to the t would be itself e to the t. Now, when you're working on free response questions, meaning it's not multiple choice, you do not have to simplify anything on the AP exam. I could leave it just like this, even with the first power in there and times the negative 1. Just write it out and walk away. The flip side to that is that if it's multiple choice, they're going to actually force you to simplify beyond anything that you would have considered simplifying. They'll bring up rules that we'll have to refresh from Algebra 2. So we have to practice both ways. If it's free response, even on my tests, leave it just like that. Don't even simplify a thing. But if it's multiple choice, you have to figure out your answer. The only thing that I could really do on this one is drop out the first power and maybe make that negative e to the negative t to make it look a little neater. Questions? Now, those of you at home, I do have the chat open if you ever wanted to pop a question in the chat. And if after a minute or so I'm not answering your question from the chat, if you want to unmute your microphone to ask a quick question, as long as the unmuting doesn't get out of control and it is just a sporadic question here and there, that's the other way you can ask a question from home. All right, let's move on. Number 3 is an example where we don't have E as the base. This would fall under the category of a B to the U. So just for lesson purposes, some of you might like this, some of you it's overkill, but I just want to make sure everybody's with me that when I see this, the base is the 7. And it's not just an X, so I have a U, which is -3 over X. So when I'm following the B to the U rule, I kind of know who's in which spot. So my derivative here is going to start off with B to the U, as is. 7, so the -3 over X, times the ln of the base. So times ln of 7. That's the base. But then times U prime. Well, if I take a look at U here, I'm going to separate that so it doesn't get confusing. If I take a look at U, you don't have to use a quotient rule, even though it's presented as a fraction. If you take a minute and simplify this a little bit, that -3, you could think of that as -3 times 1 over X, which is really like -3x to the -1. Power rule derivative, so much easier than trying to sneak a quotient rule in here. So now we can just say U prime is 3x to the -2. Questions? Is it a -3x? Here's why no. -1, that was a negative. So the two negatives made it a positive. Other questions? All right, number 4 is a doozy. This is one of the hardest questions I could come up with. To 1, review rules that I'm technically saying you should come in here remembering. And 2, putting an exponential in here. So number 4, x squared times 5 to the sine squared of 4x. What rule should I really be starting this derivative with? Product rule. Awesome. This is multiplying two functions. This is x squared is U, and 5 to the sine squared 4x, that's my V. So product rule is U V prime plus V U prime. Again, something that you have to have memorized. You're not going to get a rule sheet. So let's start our derivative. U as is. No big deal. That's x squared. All right, here we go. V prime. This is a good one. This is a B to the U. B is my 5, and U is that entire exponent. So my rule starts off with B to the U as is. So 5 to the sine squared 4x as is. The rule then says times the ln of B, so times the ln of 5. And now we've got U prime, the derivative of sine squared 4x. What rule do I need to follow to take the derivative of sine squared 4x? It's a chain rule. If you watch the Summer Academy, I like to call this type of chain rule the PTA chain rule. There's a power, trig, and an angle. So there's a power on our trig function, and then something in the parentheses is the angle. And the order PTA, which we're used to hearing for Parent-Teacher Association, is the order of our chain rule. We've got to start with the power first. Multiply down the 2. Sign to the first. This time I'm going to leave out the 1 because I feel like it would just look cluttered. And I have to leave of 4x. So that's my power. Multiply down the 2, subtract 1 from the exponent, nothing else can change. Then I have to zoom into the trig level. What's the derivative of sine? Cosine. And I have to keep of 4x. Remember, you always have to take sine, cosine, tangent of something. If you press it in your calculator, it automatically puts up a parentheses because it's saying of what? Sine by itself, cos by itself doesn't mean anything. You always need to give it an angle. In the chain rule, the angle stays the same until the very last part. What is the derivative of that angle? Zooming all the way in, another 4. All right, so let's focus a second though, because what we started with was products rule. So this was my U. This whole craziness is V prime. And now I have to finish V U prime, which is actually nice and simple. V, we rewrite it as it is. And U prime is a nice little power rule 2x. I am certainly going to say, she said we don't have to simplify. I'm not going to try and simplify this one because this was as mean as I possibly could think of. But you need to force yourself to be looking at an example as not one step, one rule. BC Calculus is going to pull as many different things into one problem as it can, and that's sort of what you have to be on the lookout for. With that said, number 5 is a super easy one if you don't fall into the trick. E cubed. How would you describe E cubed to me? Joe? If it was e to the x, then it would have to have an x or a function of x in there, right? So the x part is what's making it the function. Yeah, it's like an e to the b. And b was a constant. E is a constant. E cubed is just a constant. I could actually plug that into my calculator and see what 2.718 cubed is. It's just a number. So just like if this was 3x, the derivative would be 3. It's e cubed x, so the derivative is e cubed. So just following that example where I'm kind of saying, be prepared for the worst, everything's going to be in it. You also have to be prepared for something that is that simple and not get thrown off by it. Pay attention to where the variables are and what values we're looking at. Questions? All right. What I'd like to talk about in example 6 is that derivative as a skill is great. We need to know how to take a derivative, but we also have to know what a derivative is. Why are we doing that? Why am I taking a derivative? Well, the derivative is the slope of the tangent line. That's sort of the underlying connection of differential calculus. The derivative is the slope of the tangent line. It's called the instantaneous rate of change. It's the slope of a curve just at that one point. So you have to recognize when the question is really just asking you for the derivative, and it might be using other words. So in example 6, it says, excuse me, find the coordinates of any points where f of x equals x e to the x has horizontal tangent line. All right, horizontal line. What's the slope of a horizontal line? 0. So horizontal slope equals 0. Slope of the tangent line is the derivative. That's what the derivative is. It's the slope of the tangent line. So this question's got a lot of words in it, but it's really just asking me where is the derivative equal to 0. Horizontal tangent means that the derivative is 0. because the slope of the tangent line is the derivative, and if it's horizontal, it's got to be 0. So I need derivative of f of x. What rule should I follow? Product rule. And luckily, it's going to be a lot easier than that last one we did. So u is just the x, so that stays x. V prime, the derivative of a plain old e to the x is itself e to the x, plus v u prime. You really don't have to write the 1 at all. I just want to make sure everyone realizes I was doing a product rule, so I put the 1 in there. And since it wants a horizontal tangent line, that means the derivative equal to 0. We need to solve. So I see a GCF. So let's factor out e to the x. T time, either e to the x equals 0 or x plus 1 equals 0. Hold on a second. E to the x equals 0? I don't think so. That's an exponential function. The x-axis is a horizontal asymptote. E to the x is never equal to 0. That means my root is not coming from that piece. The only time it's 0 is over here when x equals -1. Not quite done yet, though. I secretly underlined, not secretly, but quietly underlined the coordinates when I first started reading this. Because it didn't ask me for the value of x, which I found. It asked me for a coordinate. So it's just not done. It still wants the y value from me. A coordinate is an x comma y value. Once you know the x value, you plug it into the original function, or the original f of x, for a y value. So f at -1 is -1 times e to the -1. Remember, a negative exponent shoots that e down to the bottom. But since there was a negative in the front, the whole thing would be negative. So if that's my y value, my coordinate is -1, comma -1. Oh, not over 6, but over e. -1 over e.